Welcome. This is class number 223, FRM3, Taming Embedded C. My name is Joe Drzwicki, and I lead Microchip's embedded compiler development worldwide. 25 years ago, I was named subject matter expert in the C programming language at Bell Labs, and I've been learning about C ever since. Today, I'm going to help share some of those lessons that I've learned over the last 25 years plus, and hopefully help you tame your embedded C projects. So we'll do this by talking about several different topic areas. First, we'll discuss, we need class objectives first. So you're going to have to talk about how you can do these things. Discuss the practices that we talk about today. I'm going to talk to you about some subtleties in the C language specification that can bite you if you're not careful. I'm also going to tell you how the compiler interacts with each of the architectures. As embedded C programmers, we know that the architecture plays an important role in how we write C. And finally, I'm going to go into a couple of debugging techniques that you might not know. So we'll talk about those debugging practices, and then I'll expect that you'll be able to discuss them or ask questions. So how are we going to do that? We're going to talk about some foundational practices that are true no matter whose compiler, no matter whose language you write. When you're programming in embedded C, there are some things that you just need to know. I'm going to talk about some underlying essentials, some things in the language that you have to know, some things in the definition of the language that can really get in your way if you don't know what's going on. I'm going to talk about some specifics of the C programming language that a lot of people really don't understand. And finally, I'm going to present those debugging techniques. They're very helpful, they're not very well known, and they can go a long way to help you tame your embedded C programs. And finally, we're going to have a second part of this program that presents some practical examples that give demonstrations of the points that we bring up in the first half. So when we talk about those foundational principles, what are we talking about? We're talking about being concise but not tricky. And I'll talk about all of these in more detail. The principle of separations of concerns, which is a key item in computer science literature. And we'll talk about some ways that really bears on embedded C programming. We'll talk about organization and leveling. Organization and leveling is something that you should be identifying in your design documents, and then you should follow that organization and leveling all the way through. One of my favorite topics is something I call thinking in C. I'm going to present some analogies to normal human languages, and then you'll be able to see, no pun intended, what the language is like and how it's like a natural language. Then I'll talk a little bit about object orientation. Object orientation doesn't require an object-oriented language. You can do object-oriented implementations in C if you follow a couple of rules. And finally, in this section, I'm going to talk about some non-deterministic behaviors. As embedded engineers, a lot of what we need to do is make sure that the code we write is deterministic. And there's a lot of things that some people think that they can do and have determinism, and I'm here to tell you that it's not. So let's talk about concise code. You might have heard of the KISS principle, keep it simple, stupid. And in no area that I'm aware of is this more true than in embedded systems programming. If you have simple code, it's going to be less buggy and more deterministic, and that's what you get paid for, frankly, right? So keep your code simple. I'm going to tell you a couple of more things about that, but keep that in mind. You know, when you're writing functions, a function can't be too small. Think about object orientation, and I'm sure all of you have some understanding of object orientation. And there's a class of things that you have to implement in object-oriented designs called accessor functions. And what do? They return a private value. It's one statement, okay? So an accessor function being one statement means that functions can't be too short. It's very clear what that does. When you have a 300 or 500 line behemoth, a switch statement with 400 cases in it, the opportunity for bugs to creep in is much better. Certainly one of the things that you have to be careful of is sometimes you have stack limitations, and those stack limitations can limit the number of functions that you can have. Okay, there's something called cyclomatic complexity. It's a metric. It's available in a number of open source tools, a number of inexpensive tools, and in all of the high performance professional tool sets that I know of, that will go through and will judge the complexity of the functions that you've written according to something called cyclomatic complexity. Now, when I worked at Bell Labs, in order to go into a code review, you had to submit your code to a script, and if any of your functions had a cyclomatic complexity greater than 10, you were not allowed to even start the code review. That's how serious they were about it. So when you're thinking about code, don't think about tricky. Think about clear, concise, correct, concrete. Those are the things, coherent. Those are the things that will really save your butt when it comes time to produce your product. Now, why do you want to do that? Here's a little trick. Something that a lot of people who don't work on compilers don't know. And that is, the source code is for you. It's not for the compiler. You might know of a contest called the Obfuscated C contest, where people write code that is purposely misleading and jumbled up. The compiler reads it just fine. Okay, so is clear code for the compiler? Not really. It's for you. So don't be tricky. The compiler doesn't care. Be familiar with your fellows and share code with them that you would like to read yourself. So this is all about collaboration, not competition. You know, simple code is also a justification, like I said, about accessor functions for simplicity in code. It's just the way things work. And now we'll talk a little bit about separation of concerns. Separation of concerns helps you write simple code. So what is separation of concerns? Sometimes isolation is good. Sometimes paying attention to your own business, sticking to the knitting, is the best thing you can do. Focus on what you're supposed to do, only what you're supposed to do, not what anybody else is trying to do, and make it good and clean. That's separation of concerns in a nutshell. So when you name functions, separation of concerns, if you have that in mind, becomes immediately apparent. What do you do for everybody else? Not what you own, not what is happening inside, not what algorithm you're using. If you say sort, it doesn't matter whether you're doing an index insertion sort or a bubble sort. Sort makes it obvious that you're doing a sort. And the way you do the sort is your own business and can be changed underneath without changing the interface. Live by those thin published interfaces, general interfaces. And here's a red flag, you know, something that I use a lot when I'm doing code reviews. If I see a function name with an and in it, I know that that function is doing too much and ought to be 2 or 3 or 5 functions. So do one thing, do it well. Okay, so separation of concerns, you know, why do you break things into subroutines at all, because everyone has their own responsibilities and has only those responsibilities. And if they overstep the bounds of those responsibilities, then you get in trouble because somebody's changing a variable that they have no business changing, right? So that's separation of concerns. And if you know that the sort routine is the only thing doing sort, and all it's doing is sort, when there's a bug and the sort's not working properly, you know to look in the sort routine. It makes it easy for you. Make life easy on yourself. Again, if you have an object and you have methods that operate on that object, that's separation of concerns. That object is only worried about its own thing. It helps you keep the dependency simple in your code. It enhances reusability. Sort, if all you have is sort and you have the thing that you want to sort, everybody can use it, right? And finally, it facilitates good organization, because the systems that you develop are very complex, and you don't want to have to memorize all of this detail. Organization is your friend. It helps you be familiar with the level of operation that you need to be and not worry about the details. Don't sweat the details. So in terms of organization and leveling, why do you have device drivers? Why even bother? You bother because a device driver is a nasty little piece of code. It's something that you have to smooth out the irregularities of those devices and present a nice, simple representation to the rest of the world. When you're talking to a USART, you want to set it up, you want to send data, you want to get data. You don't care about where the bits are, you don't care about how you set up baud rate generators and stuff like that. You want to keep it nice and clean, right? So if you do that, you keep that abstraction available to everybody, and you only have to write the part between the driver and the hardware if you're going to port to a different platform. Working from device drivers, which we're all probably pretty familiar with, I'm sure that you can abstract that to communication stacks. I was a network ISO OSI wonk in my day. Each of those layers of the OSI stack have particular responsibilities and no others. And it makes those stacks very nice. TCP/IP is a little bit more jumbled, but the same kind of way. Software services, sorting, those sorts of things. Everybody can use them if you use them the right way, if you write them the right way. And different subsystems in your application, if you make them so that they're generally available to anybody, then they can be reused and save you development time. So let's talk a little bit more about that. If you start thinking in abstract terms, it was one of those things that caused me a brain cramp when I first started doing it. I really wasn't tuned into abstraction, and it hurt for a while. But it's such a powerful concept over time that you will be able to think in terms of layers, and those layers will be clean and self-sufficient and separable because they're only concerned with the things that they need to be concerned about. When you're doing a design, you don't go all the way down to the code level. At least I hope you don't. You need to talk about the system that you're creating in an abstract way so that you can describe it completely, because the completeness is important. Every detail is not. Follow those abstractions all the way down through your code, and not only will the design document not be a useless relic, It will be a great way to train people. And remember, if you can't train somebody to take your place, you can never be promoted. You can never go on to another job. So unless you want to do the same thing for the rest of your life, you know, make it easy for people to come up behind you. So when something is, a particular piece of code is responsible for a particular function, only it is responsible for that function. Don't have somebody else responsible for it. Don't have, you know, there's an old saying in the object-oriented community that a friend is someone who can see your private parts. Well, those kind of friends can get you in a lot of trouble. And messing with the things that are only the responsibility of another object cause trouble, cause adhesions, cause not clean separation, not clean interfaces. So be careful with that. And finally, you know, the systems that we're talking about, we have embedded devices now that have 2 megabytes of embedded flash. No one can keep all of those details in their heads. If you're responsible for a system like this and you have a nicely organized system, you can remember the high-level details, the high-level abstractions in that design, and not have to worry about the details, and you can negotiate the whole system whenever you have a problem much easier. And that way you can also, when you've got it broken down, you can say, okay, this team over here is going to do this bit, and this team over here is going to do this bit, and I'm going to do this bit with my team. And it's nice and clean. Everybody can do a heck of a lot of development before you bring it together and integrate it. And when you do integrate it, you have clean, agreed upon interfaces that will guide the integration. And if somebody doesn't live by the interface, it becomes really apparent, especially if you use one of the debugging techniques that I talk about later. Okay, now I want to talk a little about thinking in C. I don't know, maybe some of you speak another language. I don't speak German, but Sprechen Sie Deutsch is a very simple question in German. For all of those of you who are English speakers, sprechen is speak. Sie is you. And German, which we as English speakers would capitalize, is not capitalized. So speak you German. If you brought your grammar, if you brought your capitalization, if you brought your forget spelling, over from German, a native English speaker would have a really difficult time understanding you. In French, you know, bringing, singing, loving, those things are called gerunds. There are no gerunds in French. Similarly with programming languages, especially embedded programming languages, different languages have different ways of talking about the hardware and about system organization. If you bring those constructs over from those languages, you will confuse native speakers of that language. So we're talking about C here, we're talking about taming embedded C, and I'm telling you, if you do, like somebody I once knew, go through all of the trouble of porting the Fortran 4 computed goto construct into C, you will cause nothing but death and destruction among your fellows. So if you think in C and write in C, then you at least have the ISO C specification to agree on with your fellows. And again, and I can't say this enough, source code is for you and your team. The compiler doesn't care. Don't write tricky code to make the compiler do things. Code is a document, and that whole self-documenting code thing, we won't go there because you all know that the code is the only document that survives, right? So make the code something that's readable, something that's understandable. And express the things that you need to express in the most natural way in that language. So here's a couple of other things that are entailed in thinking in C. Atomicity. Atomicity is a concept where, say you're incrementing a 32-bit value. A 32-bit value, you say, well, it's a variable, it's a long, and I'm just adding 1 to it. How much trouble could I get into? Think about if you have a 32-bit value that you're incrementing, just keeping a counter in an ISR, and you're only reading that in mainline code. If you don't ensure that the accesses to that variable are atomic, it will get corrupted on read in the most amazing ways, in the most intermittent ways that you think possible. And if you don't understand that, then I strongly suggest going to Ray Carr's class 226 FRM3. I sponsored Ray to come back this year to give that class because it's fabulous. He also talks about volatile, and volatile is a keyword in the C programming language and one of the most misunderstood keywords in the language. It does not mean don't optimize this. It tells the compiler that when the compiler is looking at this file, which the compiler calls a translation unit, that translation unit does not contain all of the details that the compiler needs to know to optimize that variable access. Again, Ray does a great job in 226 FRM3. One of the things that I see a ton in code is casting. Oh, I'm going to force this to be a this type, and I'm going to force this to be a that type, and I'm going to force this to be a that type. The casting operation, sometimes called coercion, is really not as simple as it appears. And lots of things happen, and I've got more on this in a later slide, in the C language, in the evaluation of operators and the way that those casts are applied. Don't do it. Make things the type that they need to be. And follow that type all the way through. I guarantee if you're doing a lot of casting, you have bugs in your code that you don't even know about yet. And, if all of these, if you're not there shaking your head saying, oh yeah, I got bit by atomicity, boy, it took me a long time to figure out how to protect those accesses, but now I know, and you darn sure that I'm not going to allow that kind of access without protecting it. If you're not saying these kind of things in your head, I guarantee they're biting you. Guarantee it. Let's talk a little bit about object orientation. I've alluded to object orientation a couple of times. And, you can do an object-oriented implementation in C. I've done them myself. Back in the day, there was a preprocessor called C-front that turned C++ code into C code. So you can do an object-oriented design and implement it in C, and you don't have all of the other subtleties and difficulties that you do in C++ because you're still working in C. Bjarne Stroustrup, who invented the C++ language, once said, if C is a gun that you can shoot yourself in the leg with, C++ is a bazooka that you could blow the whole thing off. Okay? So before you go to C++, realize that there's a lot of difficulties and a lot of hidden things in C++ that will make your life meaningless in an embedded situation. So you can implement objects. You know, this is separation of concerns in its very best way. There's a lot of different strategies for doing this. I really tend to like the file or translation unit as class thing. It's a little bit more than a class. It's kind of the instantiation too, because you have to keep track of the data structures in that file. Methods and functions, if you really want to have a very high fidelity representation of object orientation, then you have to do things with tables or structures of pointers to functions and stuff like that. Or you can just bypass that because it's not essential anyway. But the cool thing about it is the data hiding is fabulous. Because if you have a static file scope variable, it's private to that file. Nobody else can see it, period. Okay? And if you have a global declaration, then that's a public variable. It's really great. But the discipline, and this is the big difference between C++ and C. In C++, it enforces the discipline on you. In C, you have to be disciplined. Okay, in this section, the last thing I want to talk about is non-deterministic behavior. And like I said before, as embedded engineers, determinism is the #1 thing that we have to be concerned with. If you're doing recursion, let me tell you right now, it's always a design choice. You can always do it some other way. With an embedded processor, with limited memory, and an even more limited stack, that if you don't handle it properly, you're going to get an exception thrown and stop running right in the middle of your code. If you blow the stack with a recursion that isn't bounded properly, recursion is not great. It's not a great choice. Along with dynamic memory allocation, I can't tell you the number of times that I've seen mallocs, the M-A-L-L-O-C function, where people don't check the return value. And if it returns null, it means, you know what, you don't have any more memory, Jack. You have to check that, and you have to be aware of it. And even worse, you have to know what you're going to do when you need memory and you can't get it. So don't fool yourself. There's no free energy right now. There's no cold fusion. You know, malloc is not an infinite source of memory. Reentrancy. Reentrancy is also another great way to screw things up. If you have a function that's reentrant, or it's called from both interrupt level and mainline, and it has static local variables, it's trivial to corrupt them. And corrupting them usually means that your device is on the quick path to a reset. I get a lot of questions too about unused memory. You know, I'm a big fan of filling unused memory either with calls to a handler, or reset instructions, or some pattern that is going to get you to a safe state. Every programmer that I know has written code that had a wild pointer that you jump to, and it was often unused memory someplace, and started doing all kinds of crazy stuff. Okay, it's pretty free. There's a great fill command in MPLAB X IDE that you can use, and you can fill it with symbolic stuff. Self-modifying code doesn't really fit in this non-deterministic behavior section, but there's no place that I could think of to put it, and it's one of my pet peeves. I haven't seen it in a long time, thank goodness, in your code and other code that I look at regularly. Don't do it. It's not worth the trouble. It's tricky. It goes wrong a lot. Determinism is your #1 priority. So now I want to talk about some underlying essentials of programming in an embedded system. The C startup is something that a lot of folks don't know even exists. I want to tell you about what it does, why it does it, and how to modify what it does. Also, I want to talk to you a little bit about stack management. Like I said, stacks are very small and very fragile in embedded applications. So we have to be aware of that and take it into account. I want to talk about the difference between blocking and non-blocking services and drivers. You always have a choice when you're implementing a driver or when you're specifying a driver from someone else. And I can tell you a couple of things that are going to be really important about that. I want to talk about resets in the device. We'll talk about exceptions even later. Resets are a whole class unto themselves. And how to optimize your algorithm. You know, I know all of you have algorithms that you wish were faster, and I'll tell you some things that you might not know about that. Okay, so the C startup lives between the reset vector and main. You know, I think we all had some point in our careers where we thought that things just magically got to main, you know, right after a reset vector, jumped to main, and everything was hunky-dory, and somehow variables got initialized and all that kind of crazy stuff. Nope, sorry. It's the C startup that does all of that. It initializes the stack. If you've got a frame pointer, it initializes the frame pointer. If you've got variables that are initialized either to a value or 0, it's the C startup that does it. Usually we have what we call a data initialization template that we copy into memory if there are particular values that need to be initialized, and just do a memclear on all the zeros. For things like floating point units, DSPs, translation look-aside buffers, some of the things in CoreCon, like fractional versus integer mode, those are all set up for the compiler-managed resources in the C startup. And, you know, it's possible to have a function that you want to run before main. It's different for all 6 of the compilers that we support. You best look in the user's guide, talk to your FAE, or come to Ask the Experts if you have questions about that. Especially on the 8-bit devices, the startup code runs at a reduced clock rate. Sometimes it's as low as 500 kilohertz, if I remember correctly. So if you're expecting things to run really fast during startup, it's probably not a good expectation. And in all of the compilers, you can actually go in and implement things that you want to happen in the C startup. You got to be careful, because if you take stuff out, oh, I don't care about CoreCon, then the compiler-managed resource expectation in the uses of CoreCon, usually in the DSP in that instance, is going to not operate properly, and you won't know why. And, you know, this is one of those things that you don't go and say, oh, you know, I modified C startup. That's why it's breaking. You know, because you did that 6 months ago. You know, Mitch Kapor said, software is the only domain where you can flush the toilet in the airplane and the wing falls off. So there's no immediate connection between the event and the failure in some cases. So a lot of people have trepidation about stacks, you know, and with good reason. And we're working on some stuff in the compiler to make this easier for you to manage. So how do you size a stack? Now, when you get to have a big application, it's a passel of work. All the calls, all the nested calls, all of their formal parameters, all of the local variables that you use in the function that gets called, all the way down, plus all of the interrupts that could possibly be nested, and all of the local variables that are in your interrupt service routine, if you use any. Now, there's even more complication to this, in that if you call functions via pointer, you have to know when those functions are called and also add their depth to the call tree. And if you do recursion, this is another reason not to use recursion, because the recursion adds a variable amount of stack usage depending on how many times you recurse, right? So you can get a great call graph if you don't know about the call graph function in the IDE or in the list file from the compiler. It's graphical in the IDE, so it makes it nice and easy to use. Do familiarize yourself with that and stay tuned, because we might have a way to help you with the compiler too. Now, the 8-bit machines that we have right now complicate this further, because the return addresses, when you do a call, the return address for that call is on one stack. It's a hardware stack. It's of limited size, 16, 32 entries along that line. And if you're using XC8 with the software stack or hybrid stack mode, not the compiled stack mode, that is managed in an entirely different block of memory. So when you're calculating your stack usage, you have two different kinds of stack usage: call stack usage and parameter stack usage. Okay, let's talk about blocking. I'm sure all of you have had the experience where you made a call to a driver or you've made a call to a function, and it has it's trying to get a resource, for instance. And it just diligently sits and waits for that resource and never returns. Spin loops on something. And it never returns to you. And you could get hung there for God knows how long. Okay? That's certainly one implementation. You know, you start with spin locking on the transmit interrupt flag is certainly one very common example of that. If you have a driver that will send that character as soon as it can, and you're willing to block, that's fine. But that driver should also give you the opportunity to see if the transmit interrupt flag is available. You know, I don't remember exactly whether it's set or not set, but, you know, will the character send right away, or will I have a non-deterministic wait? There's that word determinism again. So that you can tell whether or not you want to do something else while you're waiting to be able to transmit. A lot of times this is called a wood block, you know, wood block. And the driver can return that it would block if you called it. If you're writing drivers, provide this functionality. Just don't go off and obstinately do what you were asked. Give the people who are using your services an opportunity to find out if what they want to do is going to be dispatched effectively by implementing you know, a check to see if whatever resources is available is really available. Finally, you know, every one of these devices have a number of different resets. You know, resets for different reasons. They all have different registers that say what that reason is for the reset. And I encourage you to look at this, and I'll talk a little bit more. Well, I'm talking about it at the bottom. I'll talk about it more. If you have an unprepared interrupt, if you have a trap, if you have an exception, an odd address trap, a bad address trap, whatever, at production, the default behavior for those is to reset the device. And if you don't prepare those things, which I highly recommend that you do, then when you take that reset, your only recourse is on power up, on reset, to go look through and find out the reason why you reset and take appropriate action. This is the time that you let fire out of motors and power supplies. You know, so resets are really important. It's also a great use of the C startup. You know, if you want to see if you are if you're starting up because you took a reset, then modifying the C startup to do that even before you get into main may be something that's useful to you. You know, a word about jump zero or its moral equivalence. Jump zero doesn't reset the return stack on the 8-bit devices. So if you have a maximum depth of 22 and you jump zero with 16 of them used, and you go to the 22nd level, you will have blown the return stack at the 32nd level, or only 16 further in. So you're going to get a reset. So be really careful about jump zero. Its behavior is very different. Making computations fast is really kind of an interesting topic because there's a lot to it. If you have an algorithm that needs to be fast, spend some time thinking about it. You only write it once. It runs hundreds of millions of times, right? Dig out a reference. You know, in my day, it was Donald Knuth's 3-volume epic sorting and searching database and semi-numeric algorithms. I even remember all 3 of the volumes. There's great ways to understand the complexity of your algorithm, the order notation, which you should know if you're going to do these sorts of things. And don't try to identify code sequences that are 3 instructions long that can be 2 instructions long when the overall algorithm is spaghetti and just all over the place and order n squared. Okay? When you talk about optimizing computation, if you think of the algorithm as the macro level and the instruction choice as the micro level, compiler optimizations are at the nano level. And they're only effective because they're repeated hundreds and thousands of times. I'll talk a little bit more about that. If you do pay good attention to the high level and the mid level, and you write good, clean, understandable code, that's the kind of code that the compiler is going to eat through and do a great job at optimizing. If you have code that's spread all over the world and the compiler doesn't know what to do with it, it won't do as good a job. So write good, clean code that the guy sitting next to you can understand. It doesn't matter if you can understand it. Again, you don't want to be in this job for the rest of your life, right? You want the guy next to you to take over this job. So make sure that you write it so that he can understand it. And he's not really as sharp as you are. You know, so be simple. All right, I want to talk about some language specifics now. Implementation-specific behavior is something that's mandated by the ISO-C standard so that the compiler can generate the best code that it can for every architecture. And there are a lot of decisions that have to be made to understand how the code is generated. Newsflash, an int isn't always 16 bits. I want to talk about built-in functions. I want to talk about a couple of language subtleties in the language, integral promotion and operator precedence. And I'm finally going to get to that optimization that I've been threatening you with for a while. And I want to talk about a concept called the relationship of source to binary. But I'll save my thunder. Okay, so implementation-specific behavior, like I said, is mandated by the standard and is there to enable the compiler to generate optimal code for that architecture. So all of the decisions about type sizes, how many bits is this type, how many bits is that type, what's the default signedness? The default char in XC8 is unsigned or signed. It's signed, which blows a lot of people's minds. It's in the implementation-specific behavior. Now, you should never write code that you have to know the implementation-specific behavior to make it work properly, because then you've just completely scuttled portability. The way arguments are passed, something that compiler guys talk about is the application binary interface. What's the order that they're put on? Is there padding on the stack when you're passing arguments? How do returns happen? Is there a return from main? What is the signage and type of the return to main? And here's another thing that doesn't really fit anyplace else, and don't fall for this. A pointer is not an int. And if you don't have a deep visceral reaction of, oh my God, don't I know it, especially on these embedded targets, there is often no integral type that can hold all of the information necessary to point specifically at a given variable or function. So if you say, oh, but, come down and talk to me offline, come to the compiler after hours Thursday night at 7:30, and we can talk about it. Okay, the compiler does nice things for you too. There's a lot of built-in functions, and these built-in functions are common operations that you need to do all the time. Unlock sequences, stuff like that. And the compiler knows absolutely about everything that's in every built-in, so it doesn't impede optimization. It doesn't break any of the scanning algorithms that the compiler does. They're documented in the user's guide. If you can't find them in the user's guide, come down to Ask the Experts, come down to the compiler after hours, and we can tell you more about that. And generally, they're atomic in nature, not in the atomicity sort of way, but in the, they do one thing. Built-in MAC in XC16, for instance, takes the parameters to that built-in function, built-in MAC, and puts them in to the operands of a MAC instruction. But that's all. It's not an algorithm, it's not a convolution, it's not an IIR, it's the MAC itself, standalone. And if you've done some analysis of DSP algorithms, doing a built-in MAC and then having to unload all of the parameters and all of the results is really not very efficient. So there are ways around that, which is not a topic for this class. It's a much deeper topic, but you can come to Ask the Experts if you've got some questions, or come to the compiler after hours. Integral promotion is in one of my big three of things that catch people out. In the standard, it's specified that the compiler must implicitly, and that means without telling you, convert integers from a smaller form to a bigger form. You've probably all suffered from this. There's a fabulous webinar video by my colleague Jeff O'Keefe that's in the additional material at the end of this presentation that describes integral promotion in detail. But at the high level, mostly it's with char, char, and short. And the standard's number one priority is no data loss, which means that smaller things get converted to bigger things. Like if foo is a char, tilde foo, which is the binary unary not operator, is an int. So if you say if tilde foo equals 0xff, equal 0xff, right? It's not going to. If a and b are unsigned characters, a minus b is an integer, an int, not a character. Okay? Mostly, this applies to just a few of the operators: addition, subtraction, unary, not, the shifts, both left shift and right shift, and the switch statement. And this is one of the times that you'll hear me say it's okay to do a cast if you do these sorts of things. Now another one, and this is closely related to integral promotion, is operator precedence. There is a strictly defined hierarchy of operator precedence. It's a page long because there's a lot of operators in C. Postfix, not prefix, but postfix, increment and decrement, function calls, the structure operators and the array operator are the highest. In addition to the operator precedence, there's an associativity, left to right or right to left. If you have, well, let's talk about this. It's not the same as the order of evaluation. And a lot of times in C, the compiler has the option about what thing to evaluate first. Many other times it's dictated by the standard, but it's not logical. And me and the rest of the compiler team can't change that. It's in the standard. So you have to know what's there. So if you have A divided by B divided by C, which comes first? Well, the associativity of the division operator is left to right, so it would be A divided by B in parentheses divided by C. When you look at A divided by B divided by C, it's ambiguous. But the language standard clears up the ambiguity in this way, in a way that I would particularly agree with, but not all of them do this. If you really want to force it, you can use parens to group and override all of this associativity and order of evaluation. There was a great study by the Naval Research Laboratory on the incidence of bugs, and complex if statements were the #1 cause of bugs. So you might think you know what a complex if statement is saying, but it pays to know. And a lot of times you don't because the standard is not logical. The saving grace of all of this complexity is that it only comes into play if you write complex code. Remember my first slide? Keep it simple, stupid? That saves you from all of this stuff. Write clean, clear, simple code. It'll run fast. The compiler will generate great code. The compiler will optimize it well. You win every different aspect, every dimension you can think of by writing clean, simple code. So let's talk about that optimizer. You know, I've been talking to a lot of people this last year about optimization in C. And I really prefer the word transformation to optimization because the compiler doesn't know anything about your code. Nothing. Okay, let's get that clear. The compiler knows nothing about the semantics of your code. So what does it know about? Like I said, remember I said that the compiler doesn't care about the source code? The first thing the compiler does is turn your source code into something it calls an intermediate representation. And everything the compiler does is based on that intermediate representation. It doesn't do anything with your source code other than convert it and then leave it alone. And the way compiler optimizations work is a series of tiny, 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 tiny little optimizations that it knows exactly where it can apply them, it knows exactly when it's legal, and it applies them perfectly time after time after time after time like a well-written program does. Here's an example. If you have the statement t equals 4, and then immediately after that you have the statement r equals t, the compiler can say, well, look, I know that I just put 4 in t, so I'm going to put 4 in r too. And you say, big deal. Okay, but moving a literal, remember your assembly language? Moving a literal is all one instruction. Finding out what's in t and then taking what's in t and moving it into r is a couple of instructions. Do that 1,000 times and you've eliminated 1,000 instructions. This is the power of compiler optimizations, but it's also the brain deadness of compiler optimizations. There's no thought there. When an optimizer runs, and for all of the compiler, generating correct code is the first job. And I've seen a lot of things on blogs and other places. Well, I know that that register is not used again, and so the compiler is stupid for not reusing that register. Well, you know what? There's a lot of times when the compiler knows that register is used and you're just missing it. So the compiler is really, really great at knowing when a transformation is legal and carries around a lot of baggage so that it can tell. So when we talk about optimization, you know, a good algorithm will beat an optimizing compiler by orders of magnitude every time. Something I want to warn you about. One of the ways that a compiler optimizes code size is finds out when code is never used, when it's redundant, when it can't be reached, or when it has no visible effect. How many of you have had a timing loop removed by the optimizer and completely destroyed the operation of your program? Okay? Two things. Compiler is behaving absolutely the way it should, and you need to go to Ray Carr's class, FRM3 226, on volatile and atomicity to find out why. You should put volatile on the loop counter. The other thing about transformations is there's no guarantee. we just ran the Cormark benchmark on XC16, expecting to see minus 01, minus 0, minus 01, minus OS, minus 02, minus 03, in terms of speed, increasing speed. And on Cormark, 02 is actually faster than 03. We're still looking at why, but just because you choose the highest speed optimization or the smallest code size optimization, which is minus OS, doesn't mean that that will always get you the smallest code. It means that it uses the transformations that generally move you toward the smallest code size. Finally, a lot of people say, well, I'm using the same compiler and I'm using the same source code, and I just changed the switch and it completely changed my binary. Well, you know what? You really want that. Actually, Kobus is my colleague that's going to present the second half, said he was talking to a guy in the GCC hierarchy, way up in the hierarchy, and they had an example where they compiled the same example 100 times and it generated a different binary once. And they were trying to find out why. But the source code does not completely specify the generated binary. So if it changes, don't panic, because those binaries are going to be functionally equivalent. And that's like generating correct code, something that the compiler guarantees. But you really want it because different optimizations, different versions of the compiler, ordering of data structures, all of that can collaborate to generate a different binary. But the compiler does guarantee that those are functionally equivalent. My last part today is going to be talking about a couple of debug techniques that you might know about. I want to talk about buffering and stack overflows. Who's had those? Buffer overflows really got a lot of prominence in the news about buffer overflows being a way to hack into systems. I can show you a couple of things about that. The stopwatch is a great and underused resource. I want to talk about exceptions, traps, and interrupts. I want to talk about assert, the assert macro. I'm crazy for assert, and we've got an even better replacement in finally trace and log. So with buffers and stacks, Microchip, and to my knowledge, only Microchip offers this functionality called break on data write. You can go into the hardware breakpoint, say break on data write on this location. You can specify a value that it's going to write or any value. And for instance, if you're blowing your stack and you want to know why, you put a break on data write right in the direction that the stack is growing, which is why this has got a red star on it. In the direction that the stack is growing, and as soon as you write beyond your stack, if you put a little pad over there, you will know why. You will break and you will see why that your stack is being overwritten or that buffer is being overwritten. It's easy to identify when you have a wild pointer where it's going to. We also have this new thing that just came in between last masters and this masters called conditional software breakpoint. The assert macro is a great thing, but it writes to a console. We don't have consoles anymore. Conditional software breakpoint has the same signature that assert does, but it doesn't print something to the console and exit. It just has a software breakpoint there. So you can figure out why. So if you're counting on a particular range of parameter coming in from a different function over that interface that you've agreed to, and you're really not sure about the guy who wrote that function, put conditional software breakpoints that say, If the condition is, if the parameter is out of range low, break. If it's out of range high, break. And your code will never malfunction because of a bad parameter. You catch them before they can cause harm in your system, and you can go beat on your buddy for passing you bad data. If you're catching that stack, pad your stack. If you pad it and if you fill it with a given pattern, you can always stop the debugger and look at where the pad is. And it's a little tricky to set up the pad, but we can tell you about that at Ask the Experts or the compiler after hours. If you see stuff that isn't the fill pattern in there, you're overwriting your stack. And your stack is either too small or you've got a wild pointer. Some of the devices have a stack exception. If you can, use that stack exception. A blown stack will cause you all kinds of crazy problems, and it's really difficult to track down. So use it if you can. And like I said, on the 8-bit devices, the parameter and return stacks are different. The stopwatch is great. It's built into the simulator. It's built into all the silicon. It's non-intrusive. It doesn't even use the CP0 clock on MCU30 or PIC32 devices. It's relative to the CPU clock, so you've got a hard reference. And you can do things like time stuff and see exactly how long this particular thing is running. It's really easy to do in the IDE. If you don't know how to do it, ask the experts again. It's a great resource for you here this week at Masters. And you can time anything, interrupt service routines, timing loops, whatever you want to do. Again, just like resets, exceptions, traps, and interrupts vary by architecture. Prepare all of them. The compiler will populate all interrupts, all traps, and all exceptions with default handlers, which basically do a software breakpoint. What a great relief. For those of you who have had unprepared interrupts and the thing all of a sudden just resets, and you go, okay, great, it reset. Why? If you have a software breakpoint in all of those unprepared devices you don't expect that you're using but maybe really are, and it stops in that interrupt handler, then you don't say, why is it resetting? You say, why am I getting an interrupt on USART3? I'm not even using USART3. And then you go to find out that you set the enable on 3 instead of 2, which is why you're not getting the data on 2. Okay? Again, the software breakpoint is a great thing. And you can trace back from these things. When you get a breakpoint in a trap, you can go into the IDE, again, ask the experts if you don't know how, and trace back and find out where in my code was I running when I triggered this exception. And not only do you know that you got an address exception, you know the code that caused it. What a huge difference it makes in debugging complicated problems. All of that goes away when you're running a production mode build, not a debug mode build. So these are great things to do with a debug mode build. When you're running in production, they just reset. Okay? So assert, I talked a little about assert. Assert's not optimized for embedded code because it prints to a console and exits. So we've provided this conditional software breakpoint that has the same signature and just stops in the debugger. Now, underlying that is this other thing called software breakpoint. And you can have as many software breakpoints as you need. It's just a simple program memory breakpoint. If you have one of those conditions where you say you should never get here, then a software breakpoint is really great because when you do get there, you'll be able to find out why, and you'll still have the entire memory image intact to find out why. Save those hardware breakpoints for complex breakpoints, breaks on data write, all the other great things that Microchip breakpoints do that none of our competitors do. The last thing I want to talk about is trace and log. These are macros that stream data off of the device through the debug channel. And they're very much like the old in-circuit emulators. You can set trace points everywhere, anywhere you want in your code, leave yourself a trail of breadcrumbs, and then go through that trail of breadcrumbs. I don't know how many of you have used instruction traces. When you're thinking about a device that's running at 200 megahertz and has a instruction, 2 or 3, 4 times per clock, you're talking about 800 million instructions per second. Do you want to really go through all of that data to find out where things went wrong? You know your code. Instrument points along the way, and then follow the breadcrumbs. When there's 20 or 50 or 100, you get through them a lot more quickly than if there are 800 million a second. Log is a really great thing because in addition to saying you were at this place in the code, you were at this place in the code, you were at this place in the code, log also returns a variable. So you can log the variable that you're going to switch on before you switch. And I've seen a number of times where people are getting bad data and switching on something that they don't have in their case statement, and they don't have a default to handle it, and all craziness breaks loose. So, you can do things like the hex value of a function pointer. As you get to a place where you're going to call through a function pointer, print out the address that you're going to jump to the debugger. Stream it off the device in real time, and then analyze it after the fact when you have some time. This is really a practical example. There's a really great article in the additional information section. One of the things that we wanted to talk about is saving power. Some of you might build miniatures. And saving power is kind of like building a miniature because you got to just be precise about every little bit. You got to maniacally use those power saving modes. Let interrupt wake you up from the power saving modes. Make sure that you do things like don't wake up if you don't have to. And there, the synergy between DMA modes and not waking are great. They take a little bit of understanding to do right, but it's spelled out in application notes and in data sheets. Another thing, another class we've got going is in this curriculum, the firmware curriculum is 225. Dave Ross is teaching that class, and it's all about saving power and improving performance of your application. It's a great practicum. You should check it out if you can. And certainly reducing core voltage and reducing the clock rate can save you a lot of power. There are deeper sleep modes that you might be able to remember to use. I remember a time when a customer came to me and said, Joe, I need to be absolutely certain that the battery lasts in this device for a year. And I said, well, yeah, that's probably a pretty good thing, about a year. He said, no, it's got to be exactly a year. I said, why does it have to be exactly a year? And he said, this thing is going to be on a pole in the Arctic tundra, and the road, if you want to call it a road to it, only freezes solid 2 weeks per year, and that's the only time we can get to it to change the battery. So if you really need for something to last a year, then these deep sleep modes are available. Now, the next part of this presentation is going to be some practical examples, some real code that you can see and use that demonstrate these principles that we've talked about in the first half of the presentation. My friend and colleague Cobus Van Eden is going to present that, and stay tuned for that part of the presentation. Thank you very much.